in chemistry. Okay, so let's go for it. Let's put together this mechanism. Okay, so let's see here. So what I'm gonna first do, oops, I needed the reaction on this page as well. So I'm gonna analyze this whole mechanism right here, and I'm gonna do the steady state approximation on O3 star. Steady state approximation because that is our unstable intermediate. All right. And I'm just going to write the results. So I don't have the reaction written down up here, but I'll write the results. Actually, you know what? Let's go ahead and do it. Let's say if I recopy the mechanism, yes, it's an oxygen plus, yes, oxygen plus O2, Ka, Kb to make O3 star. And O3 star is stabilized by this collisional body at Kc and becomes stable O3 plus M star. And I'm not going to worry about M star decaying back to the ground state to M because that process happens extremely fast. And when M is something inert, like a helium or something like that, its excited state doesn't matter. So we can ignore that. And that's why I don't even have a K for that reaction. Okay. So now let's put together the steady state approximation for O3 star. Okay, this is more good practice. So we know that O3 star is formed as a reactant. Okay, so that means it's a positive rate. And that's going to be Ka times the reactants times O times O2. Okay, then now it can disappear for the reverse reaction. And so that's going to be minus Kb times O3 star, because in this reverse reaction right now, O3 star is a reactant. Let's see here. And so that's two reactions involving O3 star plus a third reaction. So we need a third term. And now O3 star disappears at minus Kc times O3 star times M, and applying the steady state approximation says we can set that equal to 0. And so now, once again, we solve for what the concentration of O3 is using some algebra, taking that's all equal to 0, right? I'll just do that for you really quick. So that becomes Ka times O times O2, all divided by Kb plus Kc, all times M. So this actually is shaking out to be very similar to the bromine situation. Okay. And to make this easier, I probably could have used K1 and K minus 1 and K2, and you would have seen the results come out very, very similar. But all the same, I already made A, B's, and C's, so let's just go for it. Okay. So now what we can say is if we look at the rate of DO3 dt, so now this is my stable product, okay? There's only one place that appears, and that's in this reaction, and that goes as Kc times M times O3 star, but we recognize that O3 star, that's an intermediate. We're going to have a really difficult time determining the concentration of O3 star. And in fact, it's only going to be around for, well, we're going to have a hard time determining its concentration because it's going to be around for such a crazy short time. Okay? So instead now, we're going to take our steady state approximation, right, and plug it in just like we did before. Okay? So now that's going to be Kc times M times Ka times O times O2, all divided by Kb plus Kc times N. And so now, once again, we want to think of this in terms of a high pressure limit or a low pressure limit, okay? So I'm going to continue on with this on the next slide, okay? So I'm going to rewrite this again. O3 dt, so the stable ozone molecule, not the ground, or not the excited state, but the stable O3 product. Okay. So I can rewrite that. So I'm just, using the same equation, but I'm just doing some algebra and writing it just a slightly different way. Okay. So I'm going to write that as Ka times Kc times m, all divided by Kb plus Kc times m, all times O, all times O2. Okay? So this is actually pretty cool because in the grand scheme of things, when we look at this reaction, let me use this slide. When we look at this reaction and we think about, these unstable intermediates, right, and canceling it and getting some total reaction, okay? Our total reaction just looks like O plus O2 goes to O3, and I'll say that's occurring at a second order rate constant K2. Well, now look, I've got this reaction here, and look, this just the way I've written it in this form, it looks like O plus O2 goes to O3 reacting at K2. So in other words, all of this stuff right here just appears to be like a second order rate constant, right? Because I've got first order in oxygen atom, first order in molecular oxygen. And so all of this, Ka times Kc times m divided by Kb plus Kc times m, it just takes on the effect of a second order rate constant, okay? And so I'll remind you that Ka is second order, Kb is first order, and Kc is second order. So this is a little bit more difficult to like cancel things out and see how it all shakes out. However, we recognize because it's first order no, first order O2, all of this stuff has to be a second order rate constant. Okay, so now let's divvy this up once again into low pressure limit and high pressure limit. Okay, so let's look at the high pressure limit first. Okay, so in the high pressure limit, Kc times m will be much, much greater than Kb, okay? So again, if in the high pressure limit, m is very large, and when m is very large here, let's see, when m is very large, then that means now the way that this is going to go, because now this is slightly different than the bromine reaction, right? This O3 is stabilized by M to push it on and through to make that stable product, okay? And so now what that means is what we get here is the following. In this high pressure limit, now this value under here, right, because Kc times m is much, much greater than Kb, we can effectively ignore Kb. And now what we get is the following. It looks like dO3 dt equals. Okay, so if we are able to ignore Kb, then we recognize that all of the Kc and Km will cancel. And I just have Ka times O times O2, right? And thus Ka is approximately equal to that second order rate constant that just looks like an oxygen plus O2 goes to O3 without a third body, right? So in other words, in the high pressure limit for this particular reaction, the high pressure limit drives us to forming more product, okay? Which is pretty cool. That was the opposite of the example here in this bromine example, where in this case, the high pressure limit drives us back to more reactants. So these mechanisms are dynamic, right? High pressure limit and low pressure limit can mean different things for different chemistry, as you might expect. Okay? So let's see here. Where'd we go? So under the high pressure limit, yes, the reaction just approaches that of, I'm going to rewrite this under my high pressure limit right here. Okay, so it's just looking like O2, or O plus O2 goes to O3. Okay, so what about under the low pressure limit? Well, under the low pressure limit, okay, then M is very small, and thus now the opposite case, KB, is much greater than KC times M. All right, and so now under this reaction right here, what ends up happening is the following. Let's see here. So all of that ends up becoming DO3 dt equals. So now I can effectively ignore this KCM, right? And so this just ends up becoming Ka times Kc divided by Kb. Now all times M times O times O2. Okay? And so this is really cool. If we look at this here, in our units, a second order rate unit times a second order rate unit divided by a first order rate unit gives me a third order rate. So in other words, Ka times Kc divided by Kb just looks like this K1, 2, 3, which I described previously right here, right? So I'll write that reaction down again. So now under the low pressure limit, this just looks like O plus M plus O2 goes to O3 at rate constant K Roman numeral 3. Okay? So that is very cool. So we can see how these conditions manifest on specific reactions. All right? So now, and the final thing I'll say about this, let's see. I think I almost ran out of room. The final thing I will say, the way this all works out, all right, is as it turns out, Ka times Kc divided by Kb times M is very close to being K2. So Ka times Kc times M divided by Kb, it's approximately K2. All right, and so what that means is our effective second order rate constant, or really I should say, this becomes a pseudo second order rate constant when we consider that K1, 2, 3 times M basically just gives us K2. All right? Okay, so again, the pressure matters, the mechanism matters. As we go through and analyze our mechanisms, we can see really cool things where in some limits, all of those elementary steps are super important. Like for example, in this ozone reaction in the low pressure limit, that third body is super important. Okay. However, in the high pressure limit, it's as if that third body doesn't even exist. Okay. The reaction just goes O plus O2 goes to O3. Okay, so this is all very interesting stuff and mechanisms. Okay, great folks. So that's the end of